Charge and mass. If you recall, protons carry a single positive charge, which we represent as positive E. And the electron carries the same amount of charge, but is negative E. And both of them have the same magnitude of charge, 1.6 to the power of negative 19. And the neutron is uncharged. It's electrically neutral. The nuclei that we're dealing with throughout this chapter are often quite small, so it's very convenient to write them in terms of a unified mass unit. We'll call this an atomic mass unit. In your chemistry class, you probably use the notation AMU instead of a U. The modern symbol for the atomic mass unit is the U. Now, 1 U is equivalent to 1.660539 times 10 to the power negative 27. That's very, very precise here. We're using more significant figures than usual because many nuclear calculations look for small differences between two masses and that are almost the same. So the two masses must be calculated or specified to like 4 or 5 significant figures. And if their difference is therefore much, much more meaningful. The AMU, maybe you've known this from your chemistry class, is defined as exactly 1/12 the mass of a neutral carbon-12 atom. Now, on your AP formula sheet, they round this value to 1.66 to the power negative 27, so you can use that rounded value. Furthermore, you can alternatively write the mass of an atom in terms of this units of energy. And this is significant because later on you'll be using E equals mc squared, and if you could replace your mass, instead of being in kilograms, you could write it in mega electron volts, which is energy per c squared, and you'll see when you plug it in here, the c squared and the c squared will cancel out, and you're really going to get your energy already written in mega electron volts. Now technically this is really, you may need to do this on Web of Science, 931.49 mega electron volts per c squared. Once again, on the AP formula sheet, they kind of round it off here. Okay, it may seem kind of unusual, but these units of mega electron volts per c squared are really units of mass. Okay, let's go on to example 1. Let's estimate the mass in kilograms of one, not mole actually, now I realize it, one atom of carbon-14, which has this mass in atomic mass units. So the mass here is 14.00341 AMUs, or we write it as U in physics. If we want to convert this to kilograms, let's get a very precise answer. We're going to use this conversion here. We're going to multiply by 1.660539 times 10 to the power negative 27 kilograms divided by 1 U. And this gives us an answer of 2.325, I guess, times 10 to the power negative 26. I could probably use more significant figures. That's the mass written in kilograms, so now you know how to convert from atomic mass units to kilograms. This is on your constant sheet, by the way. Now let's convert from atomic mass units to this sort of energy units of mega electron volts per c squared, but it's really actually units of mass. So we're going to multiply by 931.49, let's use the more precise value, mega electron volts per c squared divided by 1 U. This gives you an answer of 13,044 mega electron volts per c squared. Okay, there's a reason why. Let's just show you here. If I were to kind of use Einstein's mass energy equivalence formula and just show you the different ways you can calculate the energy, which you'll be using throughout this chapter. If we use E equals mc squared now, and let's use this mass here, which is 2.325 times 10 to the power negative 26 kilograms, and multiply by c, which is the speed of light, which is 3 times 10 to the power of 8 meters per second squared. You get an answer of 2.09 times 10 to the power negative 9 joules. Remember, this is all in your regular SI units of kilograms times meters per seconds, and that's squared. It's going to give you joules. Alternatively, if we were to write this in terms of mega electron volts, we could use this one that's already written in mega electron volts. So we could use 13,444 mega electron volts per c squared multiplied by c squared, And suddenly the c-squares just cancel out. It makes the calculation a lot easier, and you have 13,044 mega electron volts of energy. And these are equivalent to each other. They're actually the same amount of energy. You just may not know that. Let me show you that. Let's say we start with that energy at 2.09 times 10 to the power negative 9 joules, and we were to convert to electron volts. We would multiply by 1 electron volt, and remember that an electron volt, there is 1.6 to the power of negative 19 joules. An electron volt is the amount of energy the electron gains when it goes through a 1 volt potential difference. And I get an answer of 1.308 times 10 to the power of 10 electron volts, which then I can convert to mega electron volts by dividing by 10 to the power 6 electron volts, which is going to give me 13080 mega electron volts. Not quite the same, by the way. You notice it's very similar. It's not the same. You have to remember that we've done some rounding. I mean, charge of electron is really 1.602 to the power negative 19. Also, the speed of light is like 2.998 to the power 8. So there's been some rounding as I went through this problem. But really, if you kept all your digits, you should end up with really close answers if you were to keep it like 4 or 5 significant figures. Okay, that's it for example 1 in our discussion of atomic mass and charge.